NPS 500 is really sophisticated time machine, if you will. It is, sensors are coordinated in picosecond time frame. In that
picosecond. That's what I just heard. Wow.
But we got to do this. So our end customers are all OEMs, all the car companies, and we wanted to make sure that this product is kind of as hassle-free as possible, so that essentially could be a kind of a simple plug-and-play, turn it on kind of a system. So there are a lot of sophisticated calibration systems inside NPS 500 that makes that life so much easier for people. But we started with the requirements, so then we pushed for a new LiDAR technology that's not been developed before, which we call solid-state Mimo LiDAR. And this is a new concept. There are multiple kind of LiDAR technologies that are out there. Obviously, the first one that was pioneered by Velodyne was the Torrent. That was the first kind of generation, and then we saw Galvo type mirrors that steer the beam, and I think Luminar is using one of those. I'm not 100% sure, but I haven't seen one opened up. So there's that, and then solid-state LiDAR is another generation of LiDAR, and then you have FMCW LiDAR that kind of is coherent in the system. So those are the kind of LiDARs are out there. Our LiDAR is completely new system. It's called Mimo LiDAR.
So it's multiple input, multiple output. Is it?
Right. That's correct. Similar to wireless Mimo technology. So a number of lasers together collaborate again in a very tight time and space that they are coordinated, that illuminate the field of view, and then we receive those field of views from multiple optical receivers. So that's why Mimo, because multiple input, multiple output.
Okay.
And then all the advanced detections and signal processing and high resolution, they're all coming from really the heavy lift that is happening in the signal processing and mathematics. So essentially what I wanted to do was that put all the components, optical components, on the cheapest platform. So we are using 905 nanometer, and then all the heavy lift, all the signal, all the resolution and the range and all of that stuff is coming from mathematics. And that's and that's why my co-founder, Professor Asibi of Caltech, and we have quite a bit of heavy lift on mathematical people in our company.
So I assume it's the optics themselves are probably almost silicon photonic type stuff that's used in a data center or something.
Yeah. The optics are the cheapest kind.
Yeah. So you've written Moore's law already. By having
right.
Yeah.
That's right. My previous two companies, I did silicon development. So, and we ship them by boatload. I mean, tens of millions a year, or maybe sometimes more than that. And so I'm fairly comfortable with the cost curve model and how to develop silicon, and that's why I combine all of this. I spent time in our past history on optics.
Sure. Yeah, exactly.
I knew how expensive they could get if you're not careful. So focus on making it really cheap. So that's how the LiDAR piece of our technology coming together. And then on the radar side, again, it's a new concept. The way we are doing it, essentially, we call our radar system SWAM, which stands for sparse wide aperture multiband system. So it's a really sophisticated multi-frequency, and that's how the see around the corner works. it's consists of 4 bands. The highest band, it would be the 77 gigahertz band.
Okay.
And that band essentially provides us resolution,
Okay.
but it doesn't penetrate. So we have the lowest band, which is the UHF band. It actually sees and goes through vegetation. It goes goes through buildings. So because also it consists of a wide aperture and it's a Mimo system, it can track. It can steer the beam electronically. So in particular ways, we've developed some really game-changing algorithms too that we achieve one of the near theoretical limits of information theory, if I have to say this a little bit. So we are hitting all of those kind of strides.
Before we leave the radar, so in a sense, just for me to kind of understand it, it's like almost you'd have multiple cameras, one looking a long ways away. That's the low frequency, that's the UHF looking a long ways away, and then you've got the really precise camera looking closely, and that's the higher frequencies, the 77 gigahertz.
I mean, you're combining telescope and microscope to get in some sense.
That's a better analogy, yeah. And then you've got in between, it sounds like.
Right, but it's not all that simple. We use machine learning and AI really to resolve, because radar is
to pull the signal from the noise, basically.
Yeah, and track it, because there are a lot of ghosts generated by radars, and we deal with also what we call multipath signals that are coming back. So we have to resolve all those ghost targets.
Sure.
And that comes through time evolution and causality that we examine. And so our framework is Bayesian framework on top of a causality system that resolves all the ghost targets, and what remains is the real one. And it happens. So before we get to the cross section, obviously, way before, maybe in 50 meters before we get to the cross section, the radar systems, all 4 bands, collaborate with each other and interrogate into the cross sections. Now, whether it's a building or a vegetation, we can penetrate and track objects. So then that's how we actually do it.
That's remarkable. Yeah. Pretty cool.
Right. Yeah. Our system has 9 cameras, so essentially sees the whole 360 degrees. As I mentioned, we are processing quite a bit of data, sensor data, approximately 650 terabit per second on over multiple chips coming in. It's actually quite impressive. We are looking at about roughly twice as much as supercollider, CERN supercollider, which is the biggest.
Oh my gosh!
Sensing. We are doing that many, and then then the software. So it's a very sophisticated, I call it time machine. Everything is synchronized, but also calibrated, self-calibrating. So we want to make the life really easy for our customers, which are OEMs. And so this is the first generation of our NPS 500. Of course, I expect this as we go forward, this thing even gets smaller, but it's already substantially smaller. So how it would look like is, it's a 2-piece system, one for front 180 degrees and the other behind, rear car of 180 degrees. So essentially overlaps sensors. All of the sensing systems, radars and lidars and cameras, they all completely overlap each other. So there's no dead spot.
No blind spots.
No.
It's very cool looking.
Yeah, right. I mean, that really depends on the car size too, so that if the car is smaller, the two can come together and become really one unit.
I see.
So it's built that way. Eventually, our goal is obviously to get integrated into the body of the car, which we can, based on our technology. And it's really simple. As I mentioned, it's a turnkey system. So all it needs a power from battery, 12 volts, and then interface to the perception engine. We provide 2 kinds of data. One is raw data or point cloud, or we fuse the data and provide fused point, essentially boxing information for targets in the field to the perception/navigation engine, and then from then on they can take it and decide how how to process.
So you would still probably have like name your brand GPU in there, running the perception software and stuff.
Right. We hope by fusing the data, we lighten the load for the perception system, so that we do a lot of grunt work in our silicons. But the perception engine has the option to get the data raw.
Okay.
So they may want to do their own processing, our customers, but also at the same time we can give them fused.